So we'll go through what we did. The scope of it, as Steve mentioned, was to look at those 8 study areas and look at them for what we previously looked at was a 10-year. Now look at the 25, 50, and 100-year design storm events and see what improvements could be made, what alternatives we looked at, and to provide a level of protection, meaning that we can tell that by a certain amount of rain there's going to be a certain amount of flooding. As you increase the amount of rain, there's going to be more flooding. So what additional improvements need to be made to reduce that risk of flooding? Once we came up with those alternates, after analyzing many different ideas, we developed conceptual plans, which are in the report, and cost estimates for each of those plans that we thought should be considered. And we'll go through the recommendations for those. As a reminder, storm sewers are typically designed for a 10-year design level. 10-year design level means a 10% chance of happening in any given year. When the water comes off of roads, houses, sidewalks, roofs, it tries to get into the storm sewer. When it cannot get in the storm sewer, when the storm sewer fills, it goes over land, whether it be through a street, through a yard, through people's backyards, and it tries to get to the lowest point. We are in a very flat area. Unfortunately, it doesn't run very well and often gets trapped in areas and ends up flooding both streets and then, as we've seen, houses. So the runoff that it cannot get in the storm sewer flows over land. How do we get that water safely conveyed so that it's not flooding people and that roads are passable? So we looked at obtaining a greater level of protection. You asked for a 25-year, but just in terms of what is that? That's a 4% probability of occurrence in any given year. A 50-year design is a 2% probability in any given year, and a 100-year design is a 1% probability. I say that because a 100-year storm, people want to think that if you have a 100-year storm in 2011, we're not going to have one till past 2100. It's 1% chance in any given year. So we could have a 100-year storm this year, next year, or in 10 years. It's a probability, a statistical number. We looked at as President Tucker mentioned, we did field investigations. We were out there while it was raining. We stopped by, talked to several of the residents, went by many streets, did a lot of observations. We also met with Steve, walked a lot of the streets afterwards. We had 857 flood questionnaires that we've reviewed since we started this project. Flood questionnaires are very useful in when the residents telling us what happened at their house. How much water did they get in their yard, in their basement, etc. We looked at all that information. We also looked at additional information provided by village staff. We had the storm sewer atlas from the village, which we put into all of our models. What does that mean? The size of the pipes, what's the slope on the pipes. And we also used Cook County aerial topographic mapping. As I mentioned, when the water can't get in the sewers, it has to run overland, so we have to rely on the aerial topographic maps to say which way is the water running, which way is the topography going. And we'll illustrate what that means. So that's the information we used in our analysis. We took that information and put together a complex computer model. The computer model was very beneficial because it's the same model we used when we looked at the 10-year event, but now we are running significantly higher rainfall amounts. We updated the hydrology, the amount of rain that occurred, to reflect the 25-year event, the 50-year event, and the 100-year event. So for the 10-year event, where it's about 3 inches of rain over 24 hours, the 100-year event is over 7 inches of rain in that same 24-hour period. So we updated the model to reflect that. We looked at different conditions. The 100-year, what we like to determine 100-year rain, 24 hours, 7.5 inches. Well, you could also have a 100-year 1-hour storm. And as the village witnessed, that July 22nd, 23rd storm event was really over 6 hours with so much of that rain coming in a 3-4 hour span. So it doesn't have to be 24 hours. When we looked at our model, we looked at all different durations, a half hour, 1 hour, 6 hours, 12 hours, etc. And whatever gave us the highest elevations, we used that. So it was what we call the critical duration. That one gave us the highest elevation, the worst results, and we went with that model. What does that model include? It includes tributary area. So when we look at an area, what actual streets, houses, everything, what's flowing to there? That's an input we put in there. How many acres of land is coming to that storm sewer? What is the size of the storm sewer? What's the slope of the storm sewer? What is that storm sewer made of? What material? all those affect how the hydraulics, how the water moves from one point to another. When we look at not only the size of the area, we look at how impervious it is, how quickly the water moves from one point to the next. And then the storm sewers have to be connected from one storm sewer to another. They might be the same size, they might be different size. You might have 3 storm sewers coming together. But all that plays a role in how the water moves from one point to the next. So the model that we have developed takes all that into account. And again, when the water cannot get into the storm sewer, it has to flow over land. So everywhere we have storm sewers, we also have to find if the water exceeds the storm sewer, it's going down this street or through these yards, and we need to find that throughout the village. And then there's some areas that are just low-lying areas where it's going to retain water and hold water, and we include that in the model area. We call those depressional areas, areas that can hold water for extended periods of time. So that's the information that's analyzed and put into the model that we use to look at these different areas. As Steve mentioned, we have the divide, the green divide shown going through the exhibit there, between down here. Everything on the west goes to the Skokie River, on the east to the Lake Michigan. We had our 8 study areas. For events greater than 10 year, we combined 2 of the study areas. These Tree Street areas that we called over here was combined with the Provident area. So this became one large area that we're calling the North Study Area, or North of Willow Road Study Area. And we still have the South of Willow Road. That hasn't changed. So that was our second area. Greenwood Avenue Study Area is another one. The Ravines, Spruce Street Outlet, the Cherry Street one, and finally the Underpass area. That includes the area both east of the railroad tracks, as well as a short area west of the railroad tracks and east of Ridge Road. So those are the study areas we had. Those are the overall drainage, the area flowing to the west and the area flowing east to Lake Michigan.